Hi, folks. Today I'm going to talk about something exciting which we are working on. Uh, like it's a continuation of my previous presentation on Gaussian splatting. Um, where we are aiming to detect deformation using modern 3D reconstruction methods. Um, so, um, what is just outline what the problem actually is. We want to detect deformations. I have just attached some notes on what kind of detection deformations we intend to detect, like over extrusion, under extrusion, over bulging or under bulging or wrapping. So the idea is if you have a set of 3D points, we can 3D points or a 3D model of the print, you can exactly point to the deformation and you can get a metric for deformation. And once you have the metric, you can do all sorts of cool stuff like correcting them during the print, having a control mechanism for the um, deposition and uh, during the print. So yeah, um, so why 3D reconstruction? So modern machine learning has made 3D reconstruction explode. It, it's extremely impressive. I have here a demo of the signature UMain 3D printed house, which I'm going to play it for you. And um, so, as you can see, it constructs really well. This is just me walking around with my phone, and I've taken 25 pictures of the house, and yeah, fed it to a model which is called master. I'll speak further on it in coming slides. So yeah, it's extremely impressive. And the top of it is not visible because I couldn't capture a top view, but the intrinsics and extrinsics, as I said, are calculated. So we go further. So what is our approach? So we want to use this modern machine learning and modern 3D reconstruction to compare actual print to expected print. Expected print can be uh, we can glean what the expected print is off of a CAD file. So we want a method to um, compare actual print to the expected print. So for that we have two techniques which we have tried out. Gaussian splatting, which we have explored previously. I'm going to go over our um, our research with that, and the one which we are excited about now is master. So which is which has come out on 2024. So yeah. So Gaussian splatting. For just a freshen up on what Gaussian splatting is like. Rather than estimating points, can we estimate Gaussians, which will allow us to have more control over the 3D reconstruction. So we initialize 3D Gaussians using desired CAD model, and then optimize the 3D Gaussians to match the observed images. So we did this all in as a proof of concept in Blender with a deformed cylinder and a real cylinder. Um, but the results are not the greatest. So here you can see there are um, like few Gaussians blown up, you can detect the deformation, but unfortunately, like we cannot threshold it so that only deformation is detected because of all the artifacts which are because of the optimization. Um, so let's. I want to just go over why that's happening. So Gaussians are they have uh, many qualities. Like they have a mean, they have variance, and they have quaternions which dictate the rotation. So we in our approach we experimented with optimization of different attributes of Gaussian splatting. So each attribute could have been would have been optimized, but since because of the texture involved in 3D printing and its repeating patterns, as they say in computer vision, we were unable to optimize it in the way we want. So yeah, that was a dead end with Gaussian splatting. So we went back to the drawing board of sorts. So we wanted to we wanted to know what exactly we need. We want an ideal expected deformation to look like so, where you have tensors pointing towards how much it has deformed to. So um, using that, we looked into master. So now uh, now we're going to talk about um, actually so we took the data. This is shot using bachelor cameras, and um, we are using two cameras placed 50 centimeters apart, pointing at a particular particular object. So we took the real data in an actual print, and we had a CAD model. So and we ran it through our the new technique, which is master, and these are the results. As you can see, it did a pretty good job of getting the point cloud of it. Again, I would like to remind you, these are without an intrinsics and extrinsics. We are asking the algorithm to predict both the intrinsics and the extrinsics, and also the point cloud. So I think I think this is pretty good result. So I'd like to go over why it produces, how it manages to produce a good result, because it's quickly evolved. The field is quickly evolving, and since master is actually based on the same uh, model as your large language models. It has the attention mechanism. It works with transformers, and on the base of that, it can capture both geometrical matching and feature-based matchings when given two images. Um, so this is newer models keep coming at a pace, and this model seems extremely promising for our problem at hand. So now that we have a good 3D reconstruction, like what we in what we think the future work is going to be is we need to create an expected model and compare the 3D reconstruction to the expected model. So now we have a CAD model. We convert that to an expected point cloud uh, by sampling points on the CAD model, and then we need a method to overlay this. I recall you guys were working with like lining up the star and the problems you faced with them. So since this is not an entire print, um, we we are we cannot perform an ICP to line up as we have discussed before. Um, so once we have that, it's pretty easy to calculate deformation. It's just vectors and at vector calculus. So once you get the deformation, we would want to use the deformation for correcting the 3D print. So like this is further down the line research. So it will allow us to have a control mechanism which will dictate how much print deposition happens at each movement, and uh, but that's further down the line. So that's about it from me. I would like to thank uh, Dil and Vikas, Professor Vikas Dhiman, for the support, and thank you. Do you guys have any questions?